Hi, so I want to tell you about my recent paper on the cold clouds as cosmic ray detectors. And the idea is potentially a new way to constrain and to study cosmic rays, low energy cosmic rays, so below GeV or so. And why may we be interested in these cosmic rays? So first of all, above GeV or so, we kind of have a good clue on the flux of cosmic rays, at least here at the sun location, because we measure them. However, below GeV or so, it's very hard to measure the cosmic rays because of solar modulation. So this is, for example, a plot from Train book. There's different models, and the flux of these cosmic rays is highly uncertain. Uh, However, they are very important because these cosmic rays are more abundant and also have higher cross-section. So that's the cosmic rays that interact with the gas, producing ionizations, excitations, heating in cold clouds, etc., and also coupling clouds to magnetic fields. So the question I want to ask is, what's the abundance? What's the cosmic ray ionization rate in cold clouds? And as I said, so far this has been highly debated. And now the new idea is to actually use cold clouds as huge detectors of cosmic rays. Say, if you like, kind of super Kamiokande floating in space in different places in the galaxy. So that's for example, an example of that. So this is our own galaxy from ESA Sky. And clouds like this one and different clouds like this, they are like parsec scale clouds in the ISM. They're cold, tens of Kelvin. And these may be used as detectors of cosmic rays. And what's the idea? This is described in this recent paper for 2020. So basically the idea is that the cosmic rays, they penetrate into these clouds, the molecular cold clouds. And what they do, they produce ionizations, but what they also do is they produce excitations of molecular hydrogen, specifically excitations of vibrational and rotational levels of H2. So the cosmic ray penetrate, it produces electrons which interact with the H2, and then they excite the vibrational level and rotational level of H2. Now, what happens next is the H2 then relaxes back to the ground state and emits infrared photon. The photon, the lines we're talking about is about 2 microns or so. So you get an array of lines in the 2 micron range. And the important point is that these lines, the intensity in these lines is proportional to the cosmic ray ionization rate, or to the flux of the penetrating cosmic rays. So here is a plot that shows the intensity of selected 4 lines of H2 vibrational states. So in this 2 micron range, these are the blue lines, as a function of the cosmic ray ionization rate zeta. You can also write this in terms of the flux of cosmic rays that enter the cloud. So if you measure these lines, you may directly set a constraint on this. And finally, if you do it over many clouds, placing clouds in different locations closer to what we think are supernova, what the sources of cosmic rays like supernova remnants, you may be able to set constraints on the sources and also potentially on the diffusion coefficient of cosmic rays. So this is a work in progress. The paper is out and the observations uh, have been just finished recently. So stay tuned. Thank you.